Okay, hello everyone and welcome back to your YouTube channel and welcome to this fantastic video today. As you must be aware, I am recording this series of video for my students that they are undertaking this course about electromechanical conversion device systems. And one of the very interesting electrical machine is the DC machine. So today I have a very simple but very interesting video related with the voltage calculation in a DC machine. What is extremely important in this video is that you understand that depending on the armature characteristics, you can have very different electrical, mechanical, and magnetic properties. So today I have this amazing but very simple and short video. Let's start reading this statement over here. As you can see, we have an 8-pole armature of a DC machine, has 1,200 conductors, and the flux per pole is 0.03 Webers. And there is a question over here. Determine the MMF generated when running at 1,500 revolutions per minute, also known as RPM. But in this case, we are considering two different types of winding. On the first question, we will assume that we are working with an armature, and as you can see over there, is a lap wound armature. And also, the second question is related with a different type of winding, and this is the wave wound. So in this case, we want to obtain the voltages, okay? Prior to solving this example, I would like to show you the numerical results, and as you can see over there, the lap winding is generating 900 volts, but on the other hand, we have the wave winding that is producing 3,600 volts. So you can see that the induced voltage, the AMF, they are massively different. And the main difference, the rationale behind this difference, the reason behind this difference is basically the type of winding. So if you want to remember, or if you must remember the physical characteristic of the lap or the wave winding, I highly suggest that you go to the slides or go to the videos, the theory videos, and watch them again. But today I will be solving this very interesting problem. So without further delay, let's start here, okay? I believe all my students, they can recognize this beautiful equation. Equation number 1 over here is giving you the calculation of the induced voltage at the armature. And in this case, you can see that the induced voltage in volts will depend on the P, that is the pair of poles, this rotational speed that is defined in revolution per second. Be careful, be careful. The rotational speed here inside this equation must be in revolution per seconds. The flux must be given in Webers, and Z is the total number of armature conductors, and C the number of parallel paths between the positive and negative brushes. So as you can see, you must remember this equation we use in question 2. I highly suggest that if you want to see more details about this equation and the use, please go back to the video number 1. However, why I am remarking here these units? Because this equation is for MKS system. That is meter, kilograms, and seconds. So be careful with the units or you will make a disaster, okay? So the first step is we know that this machine has 8 poles, but inside this equation you need to use is pair of poles. So a machine with 8 poles, we divide by 2 because we have north and south. So we obtain over here 4 poles. So be careful again, because this is another disaster if you, instead of using 4 pairs of poles, you use 8 poles. Second step is the rotational speed that is given, 1500 RPM, it's given in revolution per minute. But this equation over here, as I said before, you need to be careful because the rotational speed must be used in revolution per second. So to convert from 1500 revolution per minute, I say 1 minute has 60 seconds, so minute with minute cancel, and we obtain the magic 25 revolutions per second. So now we have at least 2 of the parameters in the right way to be used in equation number 1. So now what we need to do is basically start our calculations. And let's start with the beautiful lap winding. So you can see over here, and I already say by the theory, and you can watch again the theory, that if we are using a lap winding, well, Z is equal to P. So in this equation number 1, 2P here will be cancelled with 2P over here, and we obtain that the induced voltage will be rotational speed in revolution per second multiplied by the flux per pole multiplied by Z. Okay? So yes, we have the beautiful equation ready. So we need to substitute it here, 25 revolution per second, flux per pole 0.03 Webers, and we have a total of 1,200 conductors. And beautiful, we obtain the induced voltage for these conditions is basically 900 volts, and this is the lap winding. So simple, is very, very simple. Next step, my dear students, is we will do similar calculation, but for the case of a wave wound. So if we are using this type of winding, wave, so C is equal to, so when we substitute that in the equation, we will obtain that the induced voltage will be P multiplied by the rotational speed, multiplied by the flux, multiplied by the total number of conductors. And that is because these two cancel with these two. In other words, these two cancel with these two. And we will have 4 pairs of poles multiplied by 25 revolution per second, multiplied by the flux per pole, 0.3 Webers, and the total number of conductor, 1,200. So beautiful, we obtain the solution over here, 3,600 volts. So as you can see, there is a massive difference between the lap wound and the wave wound. And this is because there are different ways to construct the winding, and those constructions create different electrical, mechanical, and magnetic properties. However, what is important here is the conclusion. And over here you can see the conclusion, and the lap winding is quite useful when we are working with large current applications. So if we are working with a DC motor and it will be moving a massive load and we need to deliver a lot of current, the lap winding is the optimal solution. So This winding is suitable especially for high current generators and suitable for low voltage application. Because you must remember the lap winding is also called the parallel winding, because the coils, they are connected in parallel each other, and that allow larger currents to be used. However, what are the main disadvantages of the lap winding? So we will have less voltage induced in this kind of winding. And it's evident from the previous results. You can see if you are using a lap winding is 900, but if you are using a wave winding is 3600. So yes, the lap winding has one drawback, one disadvantage, and that is the low MMF. However, also is less efficient in terms of space, and that is because the location of the windings at the armature. If you want to check this, if you want to read more, please go back to your slides, your teaching material, and also go to the theory class. So this is the end of this video. I hope this explanation, you will find this explanation very useful. I try to explain to you advantages and disadvantages of the lap winding and the wave winding using a numerical example. I hope this explanation will be useful for you and you learn something about this. And if that, please give a like to the video or subscribe to the YouTube channel in order that you will be updated with the most recent videos. And also, if you have questions, please leave a comment or just drop an email to my personal account, and I will be extremely happy to help you. This is all for this video. Thank you very much for watching, and I will see you at the next one. Bye.